Welcome to Unit B of our SLAM lecture, and this will be about using sensor data or measurements to improve the robot state. So if you remember the last time, we did two things. First of all, we computed the robot's trajectory. So we used the motor signals to determine when the robot goes straight and how fast it goes straight and when it turns. And so from those motor ticks we computed this trajectory in the real world. And the second thing we did was we used the laser scan data. So these 660 values here, and we programmed an algorithm that finds the cylinders in the scene. And so if we load all that into the viewer automatically projects this cylinder, which is to the right of the robot, to here in the real world, and the next cylinder to here, and so on for all of the 6 cylinders. So in the beginning, the extracted cylinders match very well with the landmark cylinders, which are depicted as those gray discs. But as the robot turns, the radius of the curve is too narrow. And so after a while, if we go on like that, we obtain this situation. And as you can see here, the robot detects 3 cylinders in the scene and it draws them here. However, if you look at the matches, then it's most probable that those cylinders correspond to those landmarks in the real world. And so our plan is now to find out that this point actually corresponds to that one, this to this one, and this to that one. After we know this correspondence, then we can shift not only this triangle to its correct position, but also, since our robot's position is connected to this triangle, then by moving this triangle down here and turning it correspondingly, we will also find out the true position of our robot. So the first thing we'll have to do is, for a given robot position and extracted landmarks, compute the positions of the landmarks in the real world. What you see here is computed by the viewer, but since we will need the landmark positions in the real world for our further algorithms, we will have to compute that ourselves. And I programmed that code already for you, so make sure you download the files for the Unit B of our SLAM lecture, and then locate and open the file SLAM for a project landmarks. Let's just go through the code. So as usual, I import from Lego Robot, and then I've made another thing. I have put some of the functions from Unit A into a library, which is just a normal Python file which you'll find in the Unit B directory. So the filter step, compute derivative, find cylinders, and compute Cartesian coordinates. This is all routines we made during our last unit. So the actual code is quite simple. This function detects the cylinders in the scan and converts them to Cartesian coordinates in the scanner's coordinate system. And so what is returned here is just a list of tuples, which contains every cylinder that was found in the scan. Then there's a second function here, write cylinders, and basically this just writes a list of points to our output file. Now let's have a look at the main function. So in the main function I set all the constants we need. So we had a few for the movement step, which were the scanner displacement, the conversion factor to millimeters, and the robot's width. And we had a second set of thresholds, which we needed for the extraction of the cylinders in the scan. And then here the start pose is set, and those values were just given by me, and I obtained them by measuring the approximate position as given by our overhead camera. Then I load the log file, I load the motors, I load the scan, and then here is the main loop. The main loop first computes the pose from the previous pose using the motor ticks from the log file and our thresholds. So we start with this pose here, and then in every step of the loop we compute an updated pose by using the motor ticks. Then we use the function above to compute the cylinders in the scanner's coordinate system, and then we just project them to the world coordinate system. It uses a list comprehension to build a new list from the Cartesian cylinders by transforming them using the scanner to world transformation. So this transformation takes an XY point and takes the current pose and then transforms this point using that pose to the world coordinate system, and it is a convenience function that is located in the Lego log file class. And finally we print out all the results. We print out our position, our updated pose, we print out the detected cylinders, and we also print out our world cylinders, which we have just computed. So the loop consists of only two things. It computes the new pose, and then it extracts the cylinders, and using the pose it projects them to the world coordinate system. So after you run this, it will generate a project landmarks.txt file. So open up the log file viewer and load this file. And now you will see the same scene as before. We can travel along the trajectory, and for every pose, you see the landmarks which are projected from the scanner's coordinate system to the world coordinate system. And this is the very same that we had before. The only difference is that those points now were computed by our code and not by the viewer. So the next thing we'll have to do is to assign the extracted cylinders to the reference cylinders. That is, we want to associate the cylinders from our measurements to our map. So let's say this is reference cylinder number 1, 2, 3, and so on. Whereas our measurement extracted the magenta cylinders 1, 2, 3, and 4. So we want our function to find the closest reference cylinder to an extracted cylinder and then output the result as a list of tuples, so that if cylinder number 1 gets associated with landmark number 2, we will generate the tuple 1, 2, and the same for cylinder number 2, and so on for all the other detected cylinders which are close to a landmark cylinder. And as you remember, we are also having situations like this, so detected cylinder is far away from the reference cylinders, and so we don't know if we should assign it the upper or the lower cylinder here. And in order to prevent wrong assignments, we define a rejection radius. And so if no reference cylinder is inside this rejection radius, then we won't assign any reference cylinder to our measured cylinder. So and here's your programming assignment. So it's called SLAM4B find cylinder pairs. And there's only one function you'll have to implement, which does exactly what I've just explained. So it gets a list of cylinders and a list of reference cylinders and a maximum radius. This is the rejection radius. And it outputs a list of pairs. And every pair contains one association of a cylinder I with a reference cylinder J. The remaining function is essentially the same as before. So in the main function, the pose is updated, the cylinders are extracted and transformed into the world coordinate system. And then the first new thing is here, the call to your new find cylinder pairs function, which returns the pairs. Then just to visualize the result, I have made some modification down here, where I output every reference cylinder which had a closest extracted cylinder in the scan. So after you run this, it will produce a find cylinder pairs.txt file. Load this into the log file viewer, and you will see the following. So at position number 0, 6 landmarks were extracted from the scan, and they all had a closest neighbor in the map. And so as you move along the trajectory, you can see those landmark assignments. And then as we turn here, you can see that we lose those assignments, and our strategy to always match the closest point does not work correctly. So our hope is that as we move along the trajectory, if we always match our extracted landmarks to the map, and we use that information to correct our position, then we will never lose our true position in the real world. So now please program the landmark assignment.